everyone, welcome back to this course, Digital Signal and Image Processing. Hope you have gone through the syllabus and you're prepared with all the logistics, your textbook, lecture materials, and the programming software. So we will start the course with an introduction to the signals. Signals have two forms, continuous signals and discrete signals. So let's start with signals, how it is handled and processed in the digital systems. So our first lecture will involve the digital signal basics, continuous signals. Then we will move to discrete signals. If you have the textbook of Chaparro, we are referring to chapters 0 and 1. So our objectives of this lecture session is to understand how digital systems operate, because digital system means the hardware and software that deals with the signals, how they work and how they deal with the signals. The second objective is learn how a physical quantity is represented in digital domain. So how a physical information is translated to digital signals. Then compare different types of signals. So digital image processing is actually our main focus of this course, but image is one kind of digital signal. So before we go to digital image, we need to know what digital signal is. And digital signal is part of signals. As I mentioned, there are two types of signals, continuous signal and discrete time signals. And it is also dependent on the system that is processing these signals. So let's start with a discussion, an introduction to the signals and systems. So digital signal processing is a vast topic. Digital signal processing is a vast topic and very evolving topic, and there are a lot of developments, advancements in the technology that boosted up the applications of digital signals. We know the digital technologies started in early 90s with the transistors at Bell Labs. Then digital signal processors were developed in 60s. Compact disc is one of the revolutionary discoveries or inventions of digital systems, where we not only store audio data, but we can store any type of data, and it is expanded to DVD and other forms. Software-defined radio is an application is a good example of digital signal revolution. Computer control system, nowadays every system, physical system, car, your house utilities, your any kind of mechanical systems or physical system, biological system, medical systems, they are all computer controlled. So behind this control and is the digital signals and digital systems. So first question is, what is a signal, or what do we mean by a signal? So signal means some variation. So a pattern of variation of some information, or in other words, signals are variables, are the changes either in time or other form that basically represent some physical information. So signals could be, everything is signals. Now we are talking, this is audio signal, we have video signal, we have data signal. So we have electrical signals, voltages, currents, acoustic signals. We have mechanical signals, car, velocity, everything is signal, video signals. Here are some examples that we deal with our daily life, like stock prices. This is a signal how the stock is going up or down, or what is the current value. Then data signal is, everything is data. Then we see transmit waveform, either radio waves, audio waves, or other kind of TV signals. Now, so signal is a variation of a quantity with another parameter, which is called independent variable, over a range of measurement. Now, mathematically, we need to represent this thing in mathematics. So it is a function. So signal is a dependent variable, is a function of another variable called independent variable. And the most common independent variable is the time. Like every majority of signals that we see, like car speed, audio, video, they vary with time. So when we express themselves as, like, this is X is its signal, which can be anything, and T is the time independent variable. So we plot X, the dependent variable, along the Y-axis, and independent variable along the time X-axis. And this is the pattern of the signal. This is the pattern of variation. So we, from study of the physical signal, we need to come up with this mathematical model. So once we have this mathematical model, then we can play with it. So the first thing, or the first technology we involve is a transducer. So transducer is a device, or is some form of system that translates between a physical signal and electrical signal. Why electrical? Because digital systems all are electricity based, electrical based. So we need to translate this physical quantity into an electrical signal. So in real world, like we have this signal in different form. Like for example, audio, I'm speaking. So this is a pressure wave, is a variation of air pressure with time. So this is the physical signal, and this is how it varies. Now we need this transducer, which will translate the same pattern, but to a variation of voltage with time. So this voltage will now correspond to the pressure, air pressure, or the physical quantity. So transducer will translate this physical signal to the electrical signal. And when we need to produce the output, for example, when you play the music or audio, you use a speaker. So that is another transducer. So that will translate the electrical signal to physical pressure signal. And the microphone was the other device that translated the pressure, physical pressure waves to an electrical wave. Now, when we have the signal in some mathematical form, now we need to study the characteristics of the signal. So we need to classify the signal based on different parameters. So there are a lot of properties or parameters that we use to classify a signal. The first one is predictability. That means the signal, what will be the next value if you can predict, that is deterministic signal. That means we have some idea what will be the next signal. Like weather, we study the pattern, how the temperature is varying, and based on that pattern, based on the analysis, we predict what will be the temperature tomorrow. So that is deterministic, that is predictability, but in real life, the temperature could be completely random. That means the temperature that we predicted does not match with the real temperature. So in real life, actually, every signal is random. But when we generate some signal, or when we process some signal, when we put a mathematical format model, then we actually make it a kind of deterministic signal. Anyway, so based on predictability, signals could be random, completely unpredictable. On the other hand, deterministic, that we know what will be the next value. The next parameter for classification is variation with the independent variable. For example, time is the independent variable. So how this signal vary with the independent variable, continuously or discretely. So continuously means the signal is continuous in, for example, the time is the independent variable. So signal is continuous in time, which means the signal has value at every instant of time. Like audio when we are speaking, or any music, or in the environmental noise, it has value at every second, or every millisecond, or every microsecond. So that is continuous signal. Majority of the natural signals are continuous, but there are signals which are not continuously varying, which have discrete values or discrete numbers, or discrete values at discrete intervals of time. For example, if you want to count the number of cars on the street, so this a continuous example of continuous signal is car speed. You can push the accelerator, so the speed could have any value, but number of cars on the street cannot have any value. For example, number of cars cannot be 5.23. So this has discrete values. Third category is based on repetitive behavior, whether it repeats itself. Remember, the first category was predictability. If you can determine, or if you can predict its behavior at the next moment, then it is deterministic. And the next, so based on that, whether it will repeat the same pattern, that is periodic signal. If it does not repeat, then it is non-periodic or aperiodic signal. There are a lot of other categories. We may not have enough time to go over all of these. So the one category is symmetry about the origin. So whether the signal is symmetric about the origin. If it is symmetric, then even, that means it has the same value. For example, time is the independent. If time is the independent value, a variable, then it has the same variable after 1 second later, after we start the counting, and it has the same value 1 second earlier. Odd is when it has the opposite, same value but opposite opposite sign. Then finite support, infinite support. So let's start with continuity. So first category is whether the signal is continuously varying with independent variable or not. So continuous signal, as we mentioned earlier, it has values at every instant of the independent variable. So for example, this when we graphically represent, it is a continuous curve. Whatever the curve is, whatever the variation pattern is, but it is continuously varying. So that means it has values at every instant of independent variable. In this case, it is time. Example is everything is majority of the signals are continuous, like speed, temperature. Temperature varies continuously with time. On the other hand, discrete signals, and an example of a special case of discrete signal is digital signal. Discrete signal has only finite values. The second graph shows that it doesn't have value at this instance of time. It has values only at regular intervals. It could be regular or it could be irregular, but it has values only at finite instance of infinite independent variable, like population, cars on the street, etc. Periodic signal, as we discussed, it repeats the pattern after a range. That range is called the period. So we will have the same pattern, whatever pattern it follows, we'll have the same thing repeating after that interval, which is after that, say, time period. Non-periodic, there is no repetition. For example, voice signal, as we speak, we do not repeat any word or any pattern. Even if we say the same word, the signal will be different. So here are examples of periodic signal. On the left side, we have two signals that are periodic. One is the sine wave. If you see, this is the one cycle of signal. Then after this time period, it is repeating the same pattern. So it has a basic format, a pattern or mathematical form, which is repeating every after the period. Same thing with the second signal, which is a square wave signal, but it repeats the same pattern. On the other hand, to the right side of the screen, you'll see two signals. They don't repeat. So they vary. The upper one is a continuous signal, it is continuously varying. The bottom one is discrete because it doesn't have values at every instant of time. But none of these signals have any repetitions. Periodic signal in mathematical form, we write with a time period. For example, T naught is the time period in this equation. So xt is the periodic signal. It is periodic if xt can be defined in the whole time range, minus infinity to plus infinity. And second condition is there is a time period, there is a time T naught, which is greater than 0. That means it is a positive value, which is called fundamental period of xt, such that xt plus k is an integer. That means every interval of T naught, it will have the same value. So mathematically, it will have the same mathematical rule or equation after this time period. So here are some examples, like exponential of j 2t or cosine 2t, cosine pi t. So these are different examples of periodic signal. Only the last one is not periodic, because if you see it will not repeat. We will see more examples later on. Now, for a periodic signal, there are certain parameters to characterize the signal. The first one is called the cycle. Cycle means one complete set of pattern variations. For example, this is a sine wave, whatever wave it is. So if we start counting from any point, say from 0, or the starting point in time, we go it varies signal, it comes to this point, and then it repeats. If you start counting at this point, you will start going through all the variation, then after this point, it repeats. So this is called one cycle of the signal. And the time required for one complete cycle is called a time period. So this is the one cycle. The length of the time for one cycle is the time period. Now, another parameter is frequency, which is the number of cycles per unit value of the independent variable. For example, here time. So number of cycles per time. Now, for example, if you have, this is the time, say one cycle requires 0.5 seconds. So how many cycles we have in 1 second? 1 second is the unit value of time. So we have 2 cycles, right? How did we get 2? Is 1 over 0.5. So frequency of a signal is basically 1 over t. T is the time period. Or in other words, frequency and time period, they are inversely proportional to each other. So if you have a signal with longer time period, it will have higher frequency. Sorry, it will have a low frequency. If you have shorter time period, it will have higher frequency. So the longer the time period, the shorter the frequency. The shorter the time period, the higher the frequency. The most common form of a periodic signal is a sinusoidal signal. And in mathematics, it can be expressed with a sine function or cosine function. Sine or cosine, they are basically same function with just shifted in time. So, and xt is a continuous signal and time periodic signal. In general, the general form of mathematics is A. A is the magnitude. If you look at this graph, A is the highest value of that signal. It is called amplitude. So A is the amplitude, then sine twice pi ft. Lowercase t is the independent variable, and f is the frequency. Remember, we just mentioned that frequency is inverse of time period. So if you have the time period, then you can find the frequency. The frequency is measured in cycles per second. As we discussed before, frequency is the number of cycles per second, and the unit is hertz. Hertz or cycles per second. Now, if we multiply by twice pi is pi is a unique number, but in trigonometry, pi represents 180 degree. So twice pi is 360 degree. So when we multiply 360 degree, if you remember, it comes back to the origin. So it's a complete cycle. So one cycle can be represented in trigonometry by 360 degree or twice pi. So when we multiply by twice pi f, it becomes angular frequency. Then the unit is radian per second. Radian, why? Because pi is 180 degree, equivalent to 180 degree, when the pi, the unit of pi is in radian. So here are two signals. So here is an example of a signal. First, let's look at the amplitude. Amplitude, as I said, is the maximum value or peak value. And if we compare these two signals, this has a low peak value, but same frequency, same cycle. These two signals have the same amplitude, but two different frequencies or two different time period. For example, the upper one, there are 12 periods or 12 cycles in 1 second. So the frequency is 12 cycles per second, 12 hertz. Or the period is 1 over f, so 1 over 12 second is the time period of 1 cycle. This one, the time period is 1 over 6 second. That means there are 6 cycles in 1 second. So 6 cycles per second or 6 hertz is the frequency of this signal. Now, there are different units. We need to learn this because we very frequently use these kinds of units. First, for time, we use second is the common, but we use millisecond, which is 10 to the power minus 3, that means 1,000th of a second. Then microsecond, 10 to the power minus 6, nanosecond, 10 to the power minus 9, picosecond, 10 to the minus 12th. For frequency, if the time is in second, the frequency unit is cycles per second. If the time is in millisecond, the frequency will be 10 to the power 3, that means 1,000 times, so which is called kilohertz. Then megahertz, 10 to the power 6, giga, 10 to the 9th, tera, 10 to the 12th. Angular frequency is always radian per second. Now, here is a short assignment. You don't have to submit, but if you have a paper and pen, this is the signal given to you. From this graph, find the amplitude, the peak value of the signal, find the time period, that means time for 1 cycle, and find the frequency of the signal. Hope you have answered correctly. The amplitude is 50 volts. Time period is 5 nanosecond because the scales graph shows that this is the 10 nanosecond, which includes 2 cycles. So 1 cycle will be 5 nanosecond, and 1 over 5 nanosecond is 200 megahertz, which is the frequency of the signal. Now, a lot of signals are analyzed or described in terms of frequency. So frequency is, once again, is the number of cycles per unit time. So if we have 2 signals, how do we compare 2 signals? One has higher frequency, one has lower frequency. So if we need to compare the frequencies of those signals, then we can plot the signal. Here it is called time plot or time varying signal, or the signal in terms of time in the time domain, time representation. And this is called frequency representation, the signal as a function of frequency. So frequency is the independent variable. So if you look at the signal in the top, this is plotted against time, but the frequency is 6 hertz, 6 cycles per second, because there are 6 cycles in 1 second time. So if we plot this same signal in term as a function of frequency, we'll have one value at 6 because it has only one frequency, which is 6 hertz. So here we have a composite signal, or in other words, 3 signals. So the red one, if you compare, this has 8 cycles in this 1 second period. So it has a frequency of 8 hertz, and its magnitude is 10 is the unit, which could be volt, current, ampere, or anything. The green one magnitude is 5, and it has 16 cycles in this 1 second time period. So the frequency is 16 hertz. What about the third one? The blue one. If you look at the blue one, it is straight line. That means it does not vary with time. So what is the cycle then? Cycle means the time after which it repeats. In this case, it is repeating after infinity. So its time period is infinity. And if you take inverse of infinity is 0. So basically, it is a constant signal which has 0 frequency. So it has the value at 0. 0 is the frequency. So this graph is the time representation, time domain representation of the signals. And this is this representation in frequency domain. We can see the same signals, but in we see their relative frequencies. The next category we discussed is the symmetry. So it could be an even function or an odd function, even signal or an odd signal. So this is say the x-axis and the y-axis. So along the y-axis, if the signal is symmetric, it is called even signal. That means it has the same value. If you travel along the x-axis, if you travel towards positive domain, or if you travel to the negative domain, negative direction, you will get the same value after same distance. Here is an example. If you move some unit to the positive time or same unit to the negative time, you will get the same value. It is even signal. But odd signal, you will get the same value but opposite sign. So here, whatever you get here, you will get the negative of it when you travel to the opposite direction. So this is odd signal. In mathematics, we write that x of minus t. That means if you inverse the t, if you change the direction of t towards negative, you'll get the same value as positive t. But in case of odd signal, you will get the negative of the signal value that you get at the positive value of t. Now, not every signal is even or odd, or in other words, not every signal is symmetric. There are signals which are neither even nor odd, but it can still be decomposed, or it can still be written in terms of two signals, each of one will be either even or odd. So this can be mathematically shown like this. Say xt, which is any signal, doesn't matter even, odd. Say we are assuming it is not neither odd or nor even. Now xt can be written as xt, half of xt plus half of xt is xt. So we are not losing anything. And half of x minus t minus half of x minus t. This will cancel each other, so we'll get xt, same thing. But if you look at this, xt plus x of minus t, so you are adding the signal with its inverse value. So the signal will become even signal. On the other hand, if you subtract the signal from its negative value, it will become an odd signal. So any signal xt will have an even component and odd component. So this is some example. For example, xt is t minus square. If you look at the plot, t minus square, it at 0, the value is 1. 0 minus 1 square is 1. If you move to plus 1, 1 minus 1, 0. But if you move to minus 1, minus 1 minus 1 minus 2 square is 4. So it is not neither symmetric as even or not odd. But if you decompose using this relation, 0.5 xt, t minus 1 square, and x minus t means minus t minus 1 square. You will get t square plus 1, which is this signal. And if you plot it, t square plus 1 is an even signal, symmetric signal. And the other component is minus twice t. If you look at the graph, it is odd signal. So this signal, which was neither even or nor odd, but it can be decomposed into two signals. One is even and the other one is odd. So likewise, any signal, say this one is a piecewise signal. That means it has different function at different values of time. When t is positive, greater than 0, the variation follows twice cosine of 4t, like this. When t is otherwise means t is 0 or negative, it is completely 0. It is completely 0. So if you look at this graph, it is neither even nor odd. But if you do this mathematics, xt can be expressed as a summation of xe even function and odd function. And this is even because it is symmetric around the 0 axis. This is odd because it has the exactly opposite values. Now, when we have the signal in mathematical form, then we can play with it. We can do a lot of operations. There are lots of different mathematical operations. Some of them are simply addition, subtraction. So some algebraic operations. You sum two signals, add two signals, subtract one signal from another signal. Constant multiplication, you just multiply with a constant. That means you are increasing the value proportionately. You can shift in time. So x of t, if you change t by t minus tau or any value, tau is a constant value, say t minus 5. So the xt will be delayed by this value. So it will be shifted in time, delayed by unit tau. On the other hand, t plus tau, it will be advanced by the amount tau on the time axis. So on the horizontal vertical axis, there will be no change. You will not see the change in amplitude, but you will see the signal shifted towards positive or negative axis. Time scaling, you can multiply t by a constant. So, for example, simply minus 1, which is already we did, x of minus t, it is reversed in time. Now, if you multiply by a factor greater than 1, the signal will be compressed. The same value say same cycle variations, which was, for example, over 10 seconds. Now, if you multiply by 10, it will be over 1 second. On the other hand, if the multiplying factor is less than 1, it will be expanded in time. Time windowing, if you multiply by another function which is limited in time, then you will get only the value of the signal within that period of time. We can do differentiation of the signal. We can do integration of the signal. So some basic form of calculus will be involved in this course. Hope you know some basic differentiation and integration. If not, we will teach you. So these are the same mathematical operations, signal operations, but represented in graphical form or flow diagram form, that when we design a digital system, this is the signal addition. So signal system will take xt and yt and add them to produce the output. This one is signal is multiplying by a factor alpha. This signal is changing the time, either it is delaying or advancing the time. This is windowing. This is the integration or some kind of transformation, transforming the signal from one domain to another domain or one format to another format. When we do change the time, this is an example. So when t minus tau means delayed, the signal will be moved towards positive time. That means signal will be delayed. Delayed means it will take more time to come to the same value. On the other hand, t plus tau, the signal is moved towards the negative time. Here is an example. So this is the signal, given signal. If you apply t minus tau, it will be shifted towards positive axis. That means, for example, the zero crossing will be shifted to tau. But if you apply t plus tau, this zero crossing will be shifted to negative direction at tau. And minus x of minus t is just opposite of this. So here are some example, some exercises, problems. So at home, for you practice with each signal, like delay them, xt is given. Now perform by a delay operation, reflection, compression, expansion. This is the same delay operation, time operations, but this time we are representing the shifting in terms of angular distance, because as we discussed, when we multiply by twice pi, this time unit translates to angular unit, and within this sine, actually sine it works on angular variable. So this is the given signal, sine twice pi f, whatever the frequency is, plus 0. That means it has 0 shifting with the origin. That in other words, it starts right at the origin. This one is plus 90 degree. So we added plus, that means we advance the signal. So this signal moved to negative t and by 90 degree. And now, once again, one cycle is 360 degree. So 90 degree is 1/4 of a cycle. So if you compare, this is one cycle, 360 degree. This is half of the cycle, 180 degree. This is 1/4, 90 degree. So the signal is shifted by 90 degree. This one signal is shifted by 180 degree. Here are some exercise problems. If x1t is 2t and x2t is 5, then perform these operations. Y1 is 10 times x1t, just multiply by 10. Y2 is addition of these two, x1 and x2. And Y3 is Y2 shift, where time is shifted by -2. Next, let's talk about complex variable or complex numbers. The numbers that we deal with in our daily life, say this is August 27. So 27 is a number that we can realize in our real life. Today's temperature is, for example, 70 degree. 70 degree, we can realize the number. But in mathematics, there are numbers possible which cannot be realized in real life, but mathematically, in mathematics, they exist. So the numbers that exist in mathematics but not in real life are called imaginary numbers. So we have real numbers that we can realize, visualize, we can feel in our real life, and there are imaginary numbers which we cannot imagine, we cannot visualize, or we cannot deal with this. We don't see these kind of numbers in our real life. And the basic unit is square root of -1. If you do square root of 4, it is 2. Square root of 1 is 1. Square root of 3 is 1 point something. But square root of -1 is no real number. It's not possible. But mathematically it's possible. You can just simply write square root of -1. So that is imaginary numbers. Now when we add or mix up real numbers with imaginary numbers, then it becomes a complex number. So there are signals that represent both real values and imaginary values. So in graphical form, we use the horizontal axis for the real number or real variable, and vertical axis for the imaginary variable. So say this is one complex number, x plus jy. J is the unit of imaginary number, that is, which is square root of -1. So when you multiply any number by j or minus square root of -1, it is an imaginary number. So this one has x is the real value, y is the imaginary value. So this is the total complex number, or the signal value. And it has a magnitude, the length of the this line, that means the distance from origin, distance from the origin, and angular distance from the real axis. Complex numbers can be represented in two forms. One is called rectangular form. The one that we just saw is the horizontal axis for real and vertical axis for imaginary. Or when we write the number, we write real part and imaginary part separately. But the other form is polar form, because if we compare the magnitude of the line, the distance from the origin, and angular distance from the real axis, then we can deal with this number in polar form. So the conversion between a rectangle and polar form is very simple. Like if you x and y are the real and imaginary numbers. If you take square root of x square and y square, y without that imaginary operator, then you will get the magnitude. That means the magnitude of the signal or the value of the number. which is basically distance from the origin. And if you take inverse tan of y over x, you'll get the angular distance from the real axis. So these are from trigonometric rules. Hope you know. Now, exponential, I hope you know exponential of any signal. And if the exponent is imaginary, say j times theta, anything, j times x, j times theta, j times k, whatever, then it is a complex signal. It can be expressed in cosine theta plus j sine theta. That means it has basically two components. Cosine theta is the real value or real signal, and j sine theta is the imaginary value. Here are some examples you can practice by converting from imaginary, polar to rectangle or rectangle to polar, finding their values. So problems for practice, say x is 2 plus j5, y is 4 minus j2. So what is j1? j1 is real of x, real value of x, which is 2. Imaginary im is imaginary value of y, imaginary value is minus 2. Then x plus y, x times y, simply multiply them, divide them. X asterisk is conjugate. Complex conjugate is basically just changing the sign of the imaginary number. Or in other words, if you remember, the imaginary axis is the y-axis. So if you have a value, if you just inverse along the y-axis, you become, okay, you will get the complex conjugate of the same number. J is the imaginary operator, which is minus square root of minus 1. If you play with J, say J is 0, J to the power 0, anything to the power 0 is 1, a real number. J is square root of minus 1, a imaginary number. J square, if you square of this square root of minus 1, you'll get minus 1, which is a real number. So J sometimes becomes real depending on power. So J square is a real number, minus 1. J cube, J to the power 3 is minus J, again imaginary number. J to the power 4 is real number. So even powers of J gives you real numbers. Odd powers of J gives us imaginary numbers. Then some trigonometric rules, I hope you remember. Sine, cosine, tan, and there are in the inverse of sine is cosec, sec, inverse of tan, cot. The other thing is in this quadrant, in the first quadrant, all sine, tan, cos are positive, always positive. If the sine function is translated to the second quadrant, it will still be positive. But if it is translated to third or fourth quadrant, it will be negative. Third quadrant is for tangent. Tangent is always positive here. Cosine is always positive in the fourth quadrant. In electrical engineering, I hope you have learned some electrical signals. When the energy source is alternating current, then these voltage and current signals are called phasors because they are now complex. because they're represented by either sine or cosine function, which are part of a complex number. So they are called phasors, and they have phase angle, which is the uh, relative time between the start time we count. So phasors are represented by the complex numbers. So exponential of j is 0. J0, 0 times j is 0. So exponential of 0 is 1. So it is real time. Or in other words, in terms of 10, exponential of 0 is 10, which is constant value, or in electrical point of view, it is a DC signal. On the other hand, 20 exponential of j pi by 4. So this is shifted to pi by 4. Pi is 180 degree. So if you divide by 4, it is 45 degree. It is shifted in the positive direction or in anti-clockwise direction by 45 degree. And addition, subtraction you can do. So one thing, if you are doing addition or subtraction, it is better to use rectangular format, where you just add, subtract the real parts together and group the imaginary parts together, perform the operation. If you are doing multiplication or division, then use polar form, because they're two products, magnitudes times phase angle, the angular distance. So multiplication, you can multiply magnitude by magnitude and add the angles. If you are doing performing division, so magnitude divided by another magnitude and phase angle minus another angle. I hope you remember the electrical circuit, which involves different types of circuit elements. One is resistance, one is inductive components, and one is the capacitive components. So in terms of signal analysis, resistive circuit is a real time. It has only real value, but inductive and capacitive circuit elements are complex. They involve J. So when you have a circuit with both resistance and inductance or capacitance, it becomes a complex RLC circuit. So in this lecture, we try to learn some basic characteristics of signals, physical signals, and when they are, how they are represented in mathematical form. And when they are represented in mathematical form, we need to identify some characteristics, and based on characteristics, we need to classify them. So hope you have learned some basic ideas about signals, and you can now, when you see a signal, you can characterize them, you can tell them, tell why, if it is a periodic signal or non-periodic, if it is an even signal or non-odd signal. Then in next class, we'll continue with different form of signals called discrete signals. Until then, hope you have a wonderful time, and make sure you follow the lecture, you do the exercises, and get ready to do the lab and assignment. Thank you. Have a wonderful time.